this week we've been looking at all of our different kinds of bonds, right? We talked about ionic bonds a lot. Okay. What types of elements are involved in ionic bonds? I don't see that anyone needs to have their Chromebook open quite yet. Okay? I'm always telling you guys some important stuff. We're discussing some important stuff, so we're trying to fit those pieces together. What types of elements are involved in ionic bonds? Texas?
Non-metals and metals.
Non-metals and metals. Okay? So ionic, non-metals, and metals. And I can write a chemical formula for those, right? That I could have something like, let me grab a periodic table. That periodic table is always helpful. I could have something like CaCl2. Okay? This is known as a chemical formula. Now, what do I know about metals like calcium? Okay, what are they doing with their valence electrons in this situation in order to bond with the chlorine? What do you think, Christian?
Sharing.
They're sharing? No, they really aren't. Metal, calcium is a softie, right? Metals are malleable, ductile, it gives up. It only has, calcium has group 2 valence electrons, and it hands it over to calcium. In this case, it was 2 bullies against 1. 2 bullies ganged up against this calcium because there was 2 chlorines that said, hey, hand that over. Okay? So we had this, metals like to give. They become positive ions. And non-metals like to take, and they're negative ions. And that makes sense to me too. Like, people that are negative, they like to take, right? So, negative ions are formed when the non-metals take those valence electrons. Positive ions form when metals give up those electrons. Why is it that this becomes positive and this becomes negative? Well, if we think back to a neutral atom, neutral atoms have equal protons and electrons. Equal number. But we just said, hey, something's changing.
So when non-metal takes, it has more electrons than protons, and when metal loses,
so this one, when it took that extra electron, it has now more electrons than protons. It becomes negative. This one now has less electrons than protons, and it becomes positive. Okay, these are the bullies. Okay, how about metallic? What kind of elements are involved in metallic bonding? Harmony.
Metals.
Anything else?
No.
Just metals. How do I know that? Because it's metallic. Do I have a formula like the CaCl2? Can I like combine different metals that way? They share freely. Share electrons freely. And so we're always drawing this little picture like this that shows all these little positive metal ions. Remember that they give up those electrons so freely that they just like literally like floating in a sea of love. We have these hippies willing to share everything they have with any other metal nearby. And so these ones don't have a formula. These actually bond in simply percentages. And we talked yesterday how like forged in fire, we could have like different in mixtures of metals. It's just a pure mixture. Okay, no set amount, but it will gain different properties based upon the metals that are part of it. And if I want something stronger, I add a little bit more of this metal. If I want something a little shinier, add a little bit more of this metal. But there's no set thing like this. Okay? And then the last one, which is what people should have finished up notes for, is our covalent bonds. Okay? And I'm already seeing, hey, if I need to remember this, I'm seeing ion. An ion is when I'm having this extra charge because we've had this change of electrons. Okay? This is losing or giving electrons. That's how I can remember ionic. This one, how I remember, is the fact that I have simply metals. Covalent, ugh. That sounds like a big word.
Not that big.
Okay? But we have two parts to this. It's like covalent. I'm thinking this is like valence electrons. That's the only time I've ever heard valence before. And what does co mean? Like co-worker, your co-captains, partners. Your partners, you share the work, you do things together. So what happens with the valence electrons for covalent? They nicely share. Do they share with everyone around? No, they just share with their co-worker, their buddy.
The non-metals?
Okay, these share with buddies, only their buddies. Okay, they are involving non-metals only. They stick to their kind. If a metal gets involved, that's when we go back to that bully situation. Okay, and once again, I can have things that have formulas once again. Now I realized a problem that I had yesterday. Okay. Yesterday, I reached the end of class and I went, wait a second. One of the examples that I used for ionic was wrong. Because I forgot about the exception rule once again. I had used H2O when talking about ions. But is hydrogen a metal?
No.
Hydrogen is a non-metal in that alkali metal period, but hydrogen isn't an alkali metal. Hydrogen actually belongs over here. Things like carbon dioxide and water, H2O, are covalent because non-metal, 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 non-metal. And I made a mistake, and like I said, every time I make a mistake, I'm going to call your attention to it because are you possibly going to make the same mistake?
Yes.
Do you remember when teachers make mistakes?
No.
Really?
Yes. No.
Most people do. Most people are like, hey, did you see that? Like, how are we supposed to get this if she makes mistakes? But mistakes happen. Own it. Understand why you did it so you can avoid it. And I'm actually kind of pleased, strangely, that I made the mistake because I can call your attention to it. Hydrogen is a non-metal. It is group 1, but it's not an alkali metal.
I have a question. So, is there like a amount of atoms that need to be in like one formula? Like, you can just have one in.
No, you what? As far as how many can be in a formula, it's a matter of how they are giving, taking, or sharing their valence electrons. As soon as everyone has the right amount, if their outer shell now has 0 or 8, or in the case of hydrogen and helium 2, Once they have the right amount, they don't need to bond anymore. Okay? In the case of covalent ones, you know, those nonmetals get together, they share so that everyone has that 0, the 8, or if it's hydrogen or helium-2. Once they have that, they don't need to go talking to any other friends. They're like, oh yeah, we have our squad. Seriously. Now over here, ionic, once again, the bully isn't going to be bothering everyone. All he needs to do is take care of that one thing. Say, hey, hand over that electron. Thank you very much. And you know, maybe the nonmetal is hoping that, the metal is hoping at some point that the nonmetal drops it. It's probably not going to happen. This is kind of a hard thing to take care of. But once they have the right amount, they're done. And so whether that takes 2 elements together or it takes 3, because remember this was 3 atoms. We have subscripts that indicate how many atoms there are for each element in the formula. If I don't have a number after that chemical symbol, how many atoms are there? If I just say H2O, do I know how many O's there are?
Yes.
How many are there, David?
There are 2.
How many O's? No.
1 O, 2 H.
1 O. Anytime I don't have a number, we know it to be 1. We don't write it. We just know it. And so if there's no number, it's 1. If there were none, we would even have it in the formula. And if there's 2 or more, we indicate that with the subscript. So this has 3. If I have H2SO4, H2SO4 has how many atoms, Christian?
It has 2.
How do you get 2? How many different elements do I have? I have H, I have S, and I have O. And then I have to figure out how many of each do I have. The harmonies are there going 7, 7. Can you figure out how she might get 7? Is she even right?
Miss Lisa, these are so nice. Go get one before they go.
Well, hey, I plan to. He finally came and talked to me today, and I'll get it later today.
It's nice.
Oh, I'm glad. Okay, H2SO4. How would she get 7? Can you find a way to get 7? Or is she just crazy? She might be crazy. Like, hey, Miss Lisa's crazy. She makes mistakes. Oh, David thinks he knows. How would you get 7 out of that?
Okay, 4 plus 2 is 6, but then the S doesn't have enough, that's automatically 1. So 6
Uh-huh.
plus 1 is 7.
Would you agree with that, Jalen? Jaden? Sorry? Would you agree? 4 and 1 and 2 is 7. Because anytime I don't have a number, it's automatically 1. You may. Okay? So all of these situations, you know, am I sharing so that we can have a pair that, like, I take a part of the time, you take a part of the time, so that we can have the right number? Do I just take it from the nearest metal and don't look back? Or is it just going to be like, hey, you need an electron? Come get one. I have electrons for everyone. They don't hold on to them. Okay? So we had bullies, we have hippies, and we have our BFFs. Strange but true, the analogies help us. The analogies help us a ton. Now there's one thing that we haven't talked about really yet, more than any other, and it's talked about in your textbook. When we talk about covalent bonds, they also talk about something called polar or non-polar. You had a question? No. Or you were just going to add that? We said yesterday we were going to talk about that. I'm going to leave the stuff up about the covalent. Well, let's talk about polar versus non-polar. Okay? Hydrogen dioxide, no, dihydrogen monoxide.
I know the
Carbon dioxide. One of these is polar, one of these is non-polar. Okay? Are they polar or non-polar? One's one, one's the other. Ooh, some people have some good notes. Some people have some good notes. I would recommend that more people take notes. Also, like all these videos are going on that playlist. Go check out the playlist. You can access that very easily from Google Classroom. I have links to it there. How do I know? Like, some people that took some notes, I think, already had that because these examples are probably in the book. Harmony, is water polar or non-polar?
It's non-polar.
You think this is non-polar? Correct?
Yes, non-polar.
And you think this is polar?
Yeah. No. I mean, hydrogen itself is polar. I mean, non-polar. Yeah. Hydrogen itself is non-polar.
Hydrogen just on its own?
Yeah.
Okay, so you're saying that this H2 is non-polar.
Yeah.
So she's guessing that this might be non-polar, but she's not like positive. Bella, what do you want to add? You know, she's like grabbing the book. Let me look that up. It's in there. You want to know an easy way to tell?
By the
No, it actually has to do with.
Oh, it's polar. Because oxygen.
I have an easy way for you guys to tell.
So they're both polar.
H2O is polar and CO2 is non-polar.
Because the book says so?
Yeah.
No,
Did they give any reasons?
The oxygen atom attracts electrons more strongly than the carbon atom does.
That's true. Okay, pay attention. Let's look at where these things are on the periodic table. Hydrogen bonding to hydrogen. Where's hydrogen? On the left, right? On the top left-hand corner, hydrogen and hydrogen. They're in the same location. Correct? Okay, hydrogen and oxygen all the way over here. Okay, this one has just like one valence electron. This has a lot. This oxygen is a lot more electronegative. I said as we move from left to right, the number of valence electrons increases. So if I have more valence electrons, more negatives, this is more negative. Do we follow that? So if this is more negative and this is less negative, things are going to be more strongly attracted to that bigger charge. Yes. The stronger the attraction, okay, the bigger the difference from one atom to the other. If there's a big difference in electronegativity, where we just have a small amount compared to a large amount, those tend to be your polar compounds. Polar because it has, and so a lot of your ionic compounds, okay, are going to be this polar because we have a small amount of electronegativity, large amount. There's actually like periodic tables where you can just look up electronegativity, okay? And so it will show like a small amount and a large amount, and depending on what that difference is. The larger the difference, the more polar that compound is. Now, if you look at CO2, C and O are right near each other. Is there much difference in electronegativity? No, there isn't. There's not much difference at all. Okay? So for all these covalent compounds, this has a small difference in, it sounds like a big word again, electronegativity. This is negative charge caused by electrons. Like breaking that down, this is negative charge caused by electrons. More electrons, more electronegative. Okay? This one here, polar, we have a large difference in electronegativity. So why do you think H2 is nonpolar then? Why is that nonpolar? There's no difference. H and H, there's like zero difference. They're equal to each other. They're gonna share like exactly, equal. These guys, small difference, they share equal. These guys, large difference, the oxygen is going to pull those electrons a little bit closer to themselves. Hydrogen gets it a little bit some of the time, but it's going to be closer to the oxygen because, once again, these guys kind of try to behave like those bullies, even with their friends, more negative than they are. This is how these analogies help you to remember the science, because can we remember these situations? Yeah. Does it describe everything like 100% accurate? No, not quite. It's not a science explanation, but it helps us hook it into our brains so that we can remember. Okay? How about something like H2? Sorry, we already had H2. N2, nitrogen gas. Nitrogen gas, N2. Would that be polar or nonpolar? N2. N is in group 15. It's a nonmetal. Why do you say nonpolar? Okay, can you be a little bit more specific? I agree with you, but just because it's located here, is that why it's nonpolar? Okay. We're still missing something that I'm expecting to hear. I agree it's very electronegative, and I agree that it's this non-metal on this side of the table. But why is it that it's going to be nonpolar and share the way that it does?
Because they have the equal amount of negativity.
Yeah, they have the equal amount of negativity. We have not a small difference or a large difference. We have literally no difference.
Yeah.
No difference, nonpolar. Small difference, where they're close together, nonpolar. Big difference, larger difference, polar.
So how am I supposed to tell
What the difference is? Either they will tell you or you know it from the position on the chart. Like a lot of things involving H, and sometimes it also has to do with the arrangement of atoms too. So sometimes the arrangement of how they bond can make a difference. I'm trying to give you some basic rules to get you started so you can look for this. But a lot of things that are involving H may be polar. If I have things that are further apart from each other, even on the nonmetals, they can be polar. We're not going to get into arrangement yet. You might do that in other classes, whether it's your, IPC, biology, chemistry. But it's not something that we're going to go into detail here. Because this is not the complete picture. This is just, like I said, counting valence electrons. That works for these guys and it works for these guys. Doesn't work for the middle. This looking at electronegativity and just trying to look from it, where it is in the chart. This works in a lot of situations, but not everything. But helps us to understand the beginnings of their behavior. Okay? So what I'm looking for next week when I'm not here is you are fitting all about bonding on the periodic, from the periodic table into a graphic reflection. Yeah, I'm like popping today, right? I might just have to switch to a different mask. This one keeps wanting to go on me. But my ears are getting tired of this one. But maybe that'll stay. This one ear likes to fold. I guess I sleep on it that way a lot. And so it's like pulling straight off. Okay. I have a song for you guys. And what I should do is really add this to the playlist.
A song?
Yep. Are you going to sing it?
Oh, no. I cannot do it justice.
Really funny.
I have not done enough of these videos for you guys this year. There's many out there. Is this the one? Oh yeah, that's definitely the one. Definitely the one. I love these corny videos. There are so many corny science videos and songs out there. And they're parodies. Like some of the best ones, this one's not a parody, okay? But some of the best songs are when there is a parody done of like a song that you know, and they put the science in, and you're like, wow, they did such a good job. Okay, so I'll put this up on the playlist too. I have to make sure that I don't blast it everywhere else in the school. We'll see. If you need to like move a chair slightly so you can see it, I'll be coming up in just a second.
Shrugged and said, what's your pleasure, son? Are you up for electron transfer or electron sharing fun? Ionic or covalent? What kind of bonds are these? Involve valence electrons or compounds with these. Metal atoms lose electrons and become a charge of plus. Non-metals gain them happily, but negative to all of us. The opposite charged ions attract to make ionic bonds. The E and D 1.7 plus.
Okay, so this is that electronegativity difference again. Ionic, you can see that there is this large difference, super large difference. They're like highly strong. Polar covalent, still strong. Non-polar, they're not as strong. Okay? The things where we have greater difference in the negativity of those atoms, that's when we're getting our stronger and stronger bonds.
They dissolve real well in ponds. Ionic or covalent, What kind of bonds are these? Covalence electrons. And bond compounds with these.
So it is cheesy.
Ionic or covalent. What kind of bonds are these? Covalence electrons and form compounds with these. If E and D is 0.5 or more, the two non-metals had, you have a polar covalent bond. One atom's happy, the other sad. The atom with less En gets a positive charge that's light, and the other more greedy atom.
So that little weird symbol, it's a lowercase Greek delta, just showing partial. It's kind of partly positive, partly negative. It's not a complete, transfer the way that it is for ionic.
If E and D is 0.4 or less, two non-metal atoms bond with equal pull on electrons. Each atom is equal bond. No charges will develop, and because of that, no poles. That's why the bond is called nonpolar. On and on and on and on we roll. Ionic or covalent. Now it's easy for you to tell. Just look up the E and D, and you will do really well. But yeah.
So literally with that, there are charts out there where you can look up, okay, this atom, what is its electronegativity? This atom, what's its electronegativity? You perform subtraction and you can see, oh, well that's, a relatively large number. This is a relatively small number, but you can see that those numbers really weren't that large. It's just the fact that anything that's between 1.7 to 3.3, those are our ionic ones, from like 0.5 or so to 1.7. So what we're concerned about is roughly, if it's something closer to 0.4 or less, I don't know where you guys are going. Like, there's a whole lot of class left. Seriously. And I decided that I wasn't going to take it away from the rest of class to stop you guys, because I was about to give you guys some time to work on your own, but apparently we're packed up for the day. Don't know why. Class ends at 10:22. It's 10:05. So halfway through the class, you're packed up, ready to go. Okay? So small difference is going to be far less than 1. Closer to 0.4 or less. Okay? If we have something that is greater than that, it's going to be polar, covalent, or superpolar. If we have this, positive and minus, where they're going to try to exchange entirely. Okay? What I was literally about to do was tell you guys, hey, you have a bunch of stuff that you need to work through. All of this stuff needs to get done before you start working on your graphic reflection. If you work through this and you're ready to start looking at the graphic reflection, you can. Otherwise, you should be working through. Remember that I'm not taking a quiz grade, but I want you to look at the questions, try your best, give good answers, and look at the feedback. Okay? Follow through on the rest of these materials. So you might need that Chromebook back out.